let's get started. Okay, let's get started. Today's speaker is David D'Anteria from CERN. He's been at CERN for practically forever, or at least since his younger days. And he's worked on a whole bunch of things, FTC and UPCs with CMS, and today he's going to talk to us about some 2-photon UPC results. David.
Thank you, first of all, everybody, for being here. I will be discussing photon-photon collisions at the LHC. So I will be basically discussing these two types of, or three types of diagrams. Thank you. Basically, a proton or an ion. Thank you, Sean. So a proton or an ion collide not hadronically but electromagnetically through a photon exchange, and they produce a central system. Can be a pair of leptons, a pair of charged bosons, a pair of quarks, could be top quarks. They can also produce pairs of electronic bosons, photons, WZs, or they can produce spin 0, spin 2 resonances. So any quarkonium, but also Higgs or ALPS or graviton-like particles or ELN. So I will be discussing what we have learned about this type of physics since 15 years at CERN at the LHC. And I will be mostly covering gamma UPC Monte Carlo, which is a Monte Carlo I developed with Huachen. And I will be mostly covering CMS results. I will be showing also results from other experiments, but those are the topics I'm more familiar with.
May I have a quick question?
Sure.
Why LHC stop?
Yeah, sorry, this is this disclaimer.
Disclaimer. Oh, yeah.
Disclaimer.
Sorry.
I'm trying to, okay, it's asking me to, okay, yes. Let's go to the, so the LHC is not just the highest energy parton-parton collider, it's also the highest energy photon-photon collider. This is so because we have that, well, the charge that we accelerate at very high energies have an electromagnetic field that can be, the Weizsäcker-Williams approximation can be considered as an equivalent photon flux. So the interaction of ions or protons at large impact perimeters can be considered like a collision of two photons producing a central system. And the interesting thing is that the cross-section to produce any central system by a gamma-gamma goes like the C square of each charge. So this goes C to the 4th, which means that for lead, this is a factor of 50 million. So it's a huge cross-section, as you will see. And also, there is a dependence of the photon flux on the log of the Lorentz gamma factor to the cube power. So there is a faster than log dependence of central mass energies, log to the cube. So it's significant going from ring to the LHC also because of the higher energies. Now the two photons exchange are quasi-real because in order for the charge to maintain its integrity, they cannot emit a photon larger than the radius of the charge. So this limits the, if the protons or ions survive, this limits the maximum virtuality of the photon to about 30 MeV for lead or 280 MeV for proton. The photon energies, maximum energies, is 1/r also, but now boosted by the Lorentz gamma factor, which is very large, 3,000 for lead and 7.5 thousand for PP. So we get maximum photon energies more or less up to 80 GeV per ion and 2.5 TeV per proton. So this means that we can probe in lead we can probe photon energies up to 160 GeV. In proton lead 2.6 and in PP 4.5 TeV. So you see that this is a unique photon collider. Nobody has ever explored those photon energies. And then because of Landau-Young theorem and C's parity symmetry, the fusion of two photons can only produce a spin 0 or spin 2 resonances, or spin even, spin 4 also.
But the photon can be also polarized photon, right?
The photon is quasi-real and has a polarization indeed, but in principle, I mean the ions at the LHC or the protons at the LHC are unpolarized. So if they were polarized, then yes, you could have an extra degree of freedom, but that's not the case. But
So
they
what
are,
you're saying the production mechanism is not polarized? Are the produced photons polarized?
if the produced photons were polarized, the photons would, I don't know exactly what fraction of it would get propagated into the photon flux, but you know that, Spencer?
Well, I mean, the photons are polarized linearly along, along the direction of emission, so pointing toward or away from the nucleus. When you go through the calculations, you can, for two ion positions and the gamma position, and you consider cases of photons parallel and perpendicular, and mostly it all comes out in a wash.
So you basically lose any effect of polarization because you can't select.
You lose most of it.
So you can't, it's not really usable for your freedom.
If you were, it has not been used. You might be able to.
Are there kinematic selections, say, for some orb rapidity in P-LED where you can choose some polarization state in some biased way? Or?
Not that I know of.
Okay, so with these photon fluxes, we have a rich and unique standard model and also BSM, photon physics program with UPCs of the LHC. I already mentioned those two diagrams, but there are many studies. I mean, gamma to the leptons, gamma to tau to constrain G minus to tau, the anomalous electromagnetic moment of the, magnetic moment of the tau lepton. I will be discussing this. Light by scattering, production of exotic QED atoms, the tauonium, for example, production of scalar and tensor harmonia, botomonia, you name it. W for anomalous quartic H coupling. You can, the Higgs in principle, like we can discuss that. TT bar to constrain also top quark electromagnetic couplings, and even BSM. So any charged particle, supersymmetric or others, charged Higgs bosons could be in principle produced. And again, because of this selection rule of even spin objects, this is a good way to produce objects like axion-like particles, graviton-like particles, radions, monopoles. Monopoles are another thing. But okay, there is a broad variety of final states that one can draw. So what was the situation in terms of Monte Carlo event generators up to 2 years ago? The situation is that we had Starlight developed by Spencer and Joachim already 25 years ago. Then Super Chic more recently, an FPMC. This is for PP mostly. There were other dedicated Monte Carlos for gamma to the leptons. But a few years ago, we discussed with Huashan and we realized that, you cannot produce an arbitrary final state because, of course, this has hard-coded processes. There are many, but not all you can think of. For example, magnums are considered uninteresting and you don't produce them. They're all leading order, QED and QCD. And what we decided to do is to develop a new tool, which is called Gamma UPC, which features many interesting things. This is an automatized code that allows to generate, you can interface it with any event generator like a MatGraph or Heliconia for Quarkonia for the matrix elements. And then you get the photon fluxes and the survival probabilities and so on. So let me tell you what we can do with this code. As I said, we can produce any arbitrary final state if you interface it with any matrix element calculator. You can produce n photons or gluons in the final state. So if you have a FSR for photons, or if you had here quarks, you could emit a gluon out of the box. You can extend this to NLO, QCD, and electroweak. We have an LHC output, and then on the LHC output, you can run Pythia, Herwig, or photos for final state radiation, shower, hadronization, decays. You can do whatever you want with the final state that you produce here. And we also implemented two different form factors, two different types of photon fluxes, and also two different types of Glauber, Econal and Monte Carlo, and so on. And we called it any combination PP, PAAA for NEA. So those are the basic ingredients. We have the key properties are the matrix elements that come from an outside code, MatGraph. In principle, we interface it to MatGraph and to Heliconia or to custom codes that people are using Gamma UPC with other type of calculations, for example, line by line, like NLO, QED, QCD. The matrix elements is computed outside of the code, but the form factors, we have two, charge form factor and electric dipole form factor under corresponding photon fluxes, and we also encoded proton and ion survival probabilities. We started with optical Glauber, but then we also parameterized Glauber Monte Carlo. Is more realistic, as I will show you. So let me start one by one with these ingredients, and then I will show you the data, how it compares to these and other predictions. So we have two types of photon fluxes. The electric dipole is the same as a starlight, and the charge form factor, this is the same as supersheet, basically. And they basically, you have here the shape. So this is a function of impact parameter. This is for a photon of 2 GeV emitted from a nucleus of 200, so 5.5 TeV, center of mass energy. You see here the EDFF. The photon flux is divergent at B equals 0. So you need to put a cutoff. The charge form factor, on the other hand, is well behaved. It goes to 0 at B equals 0. So it's more realistic theoretically. So what people do is basically they implement starlight does is to put a cutoff here, which corresponds to the radius of your nucleus or your proton, but that introduces some arbitrariness. And then you cannot compute either collisions where the electron final states where one of the photons would be inside the other nucleus. So that's a disadvantage.
Make a comment or question.
Sure.
So, I mean, the reason we did that is we were thinking about hadronic final states, where, you know, if you produce a pi zero or something in the middle of the nucleus, that nucleus is not going to survive intact. You know, whereas for electrons, you produce electron-positron pair, probably will survive. Is there any hope of a more nuanced approach, you know, not using a cutoff, but also assuming, you know, calculating some nuclear survival probability when you produce something inside of it?
You will see that this is the other ingredient, one of the other ingredients of the model, the survival probability. But I think we already have it. Why don't we use the charge form factor? I mean, this is well behave going to be equal 0. So in principle, this doesn't. You don't need to worry about anything. There is an arbitrariness here. You put it at 7 Fermi, 7.1, 6.9. What I mean, so it's all these things it was, of course, 25 years ago it was perfectly, but since now we are doing things with a few percent uncertainty, I think we have to start to improve also our photon fluxes.
But there's two things. One is the photon flux. So you can calculate the probability of producing a pi zero. And I agree with you, charge form factor makes sense. But there's also the problem of what happens after you produce that. You know, if you produce something that will blow the nucleus to bits, you know, then that
sounds like really complicated old school nuclear physics.
Yeah.
Gravitron physics.
I mean, you know, there are, you know, for the EIC, there are people that worry about things like that. Is there some simple way you could do that might be a better model than either of the extremes?
Let's
you accept them all, or you?
No, I think you accept them all, and then you put a proton or ion survival probability, which is the next thing. Okay, let me comment on the proton. For the proton, we use the charge form factor also, which is called dipole form factor. Well, it's called, it's a dipole form factor, but then we realized that this is not very relevant. But there is a tail in the photon flux of the proton, which goes to high virtualities. And here, as you know, in the last 15 years, there has been lots of studies about the proton radius puzzle, where different measurements get different results from EP data or muon data. And there were new measurements by A1 and PRAD, and that extended the electron-proton elastic data. And now, so we incorporated this new data also for the proton profile. So this is our fit with uncertainties. It plays 1% role, because this is really the tail. Our photons are here, are real, quasi-real photons. This is in the tail where there is this deviation from this dipole form factor. But it's in the code also. This is 1% effect. Now this is the other thing, is that what we try to do is that we try to avoid that the two ions or two protons interact, because otherwise the final state is not exclusive. If they touch, they will interact also electromagnetically and hadronically, and they will break up. And your photon-photon system, you don't see it because it's swamped in the hadronic final state. So what you need to do for this is to include a probability of the the two ions, the two protons do not interact. And this, so this is the effective two-photon luminosity. It's just the integral over the two photon fluxes times, as a function of impact parameter, times the probability that they do not interact. And this is parameterized. I think you were the first to propose this, but okay, this is in the literature. Is that the standard iconal? Okay, so this is the explanation of the number of collisions. People doing nuclear heavy ions know what I'm talking about. And for proton nucleus, the same. So we use either the nuclear overlap or the nuclear profile function, and then times the sigma inelastic. Sigma inelastic, we parameterize it with this functional form as a function of square root of s, and that's our survival probability for the ion. For the proton, we use the Fourier transform of the elastic amplitude of the proton, and this we take it from the existing data of the elastic slope. Sorry, this is the next one. So this is the elastic slope measured at different energies. This is from Totem, for example, at the LHC, and we fit it and we plug it there, and we take this object as the probability for the proton to survive interaction as a function of impact parameter. So let's give us, after all the formulas, let's give you a bit of a feeling of what we are discussing here. How peripheral are the ultraperipheral collisions at the LHC? So what I'm plotting here is the average impact, okay, the average transverse separation of the ions as a function of the center of mass energy of the photon-photon collision. So, so this is the electromagnetic field. If the two ions are too far away, the photon-photon collisions are very soft. If they get very close, naively, you will almost touching, the electromagnetic field is very intense, and the photon-photon collision will be very high. So you see it here. So for interactions that produce photon-photon giving an object of 1 GeV, on average, okay, this is a very asymmetric distribution. This is first quartile, second quartile, and so on. But to give you an idea, that's the median of the distribution. You see that for 1 GeV, the ions are about 200 Fermi away. Okay, and as if you want to produce a very heavy system, say if you want to produce the Higgs boson, you see that this is the limit where the separation is the double of the radii of the ion, so they're basically touching each other almost. Okay, so up here, so you see it here. Below 5 GeV, the average separation is 100 Fermi. Above 100 GeV is 20 Fermi. And if from this you can also think in terms of survival probability. So that's this expression here is the two-photon luminosity, taking into account the probability of non-overlap and without it, an inclusive one. And you get this. If one, it means that 100% of the time the two ions survive. So you see that for a system below 5 GeV in photon-photon collisions, the ions do not overlap 90% of the time. If you go to a very heavy system, they overlap less than, so they overlap more than 50% of the time. The same for the proton here. So for mass, low mass is below 10 GeV, the two protons are 50 Fermi away on average. For 1 TeV now, take a look, photon-photon at 1 TeV, they are close, they are about 3 Fermi away or less.
What do you mean by proton-proton ultraperipheral? In ultraperipheral in PP interaction?
Yes, we're doing photon-photon physics, you will see. We actually set the best measurement of the G-2 of the tau lepton using proton-proton, photon-photon.
You mean they are elastic scattering?
Yes.
They're elastic, but not necessarily emitted by photon. Could be some other.
No, they are photon-photon interactions.
Yeah, but how do you know?
Well, if you produce, I will show you later on, but if you produce gamma-gamma, for example, sorry.
Oh, you look at the final state.
The final state is exactly back-to-back, and there is no other particle produced. So the two protons survive. We can even tag them in proton taggers. So there are different ways I will show you, but basically the central system is at rest. So if there are two, they decay back-to-back. If they are photon produced, the two protons survive. We can tag them. And also, and of course, the two protons, and there is no activity around the photon interaction. So the two protons do not produce anything else. So yes, I will show you things up to very high energies. I will show you that we have constrained gravitons up to, and axion-like particles up to 2 TeV with PP.
Oh, does it? The impact parameter essentially is your model, and sort of like optical model.
Yes, but this is in this case is parameterized by the transfer Fourier of the elastic amplitude. But okay, yes, it's the same idea. So survival probability: the protons survive 90% of the time, producing central system of 10 GeV, and at above 1 TeV they still survive most of the time, which is very surprising. So you can produce a gamma, you can have a photon-photon collision with an object, producing an object of 1 TeV, and the two protons survive. So thanks to the c⁴ boost, gamma-gamma luminosities are much above the pp1. So this is the gamma-gamma luminosity versus center of mass energy of the photon-photon system. This is p-LED, p-LED, pp. You see that there is this factor of 50 million that I mentioned. This is for lighter ions. And the uncertainties on the charge form factor, we vary them, varying the radius, the diffusivity, sigma inelastic, and so on. They are very small, below 1%. At low mass, high mass here, maximum 5%. For protons, low mass 1%, uncertainties, high mass 4% also. Although here we should be fair that for a proton is a more complicated object, the survival probability of a proton. There are alternative models, for example, supership. When we can compare supership to our model, we find differences of 5% here. So, okay, 2 to 5%. So this is within our model. It's not the full parametric uncertainty, I would say. Okay, so now let's take a look. This is again the same thing, the effective photon-photon luminosities as a function of the photon-photon system center of mass energy. And what you see here in blue is the photon-photon luminosity in LED. What you see here in black is the proton-proton luminosity. And now you see that there was a factor of 50 million. So what happened here? It happens that, of course, we have much more luminosity in PP than in LED. So they
almost coincide.
They almost coincide, except at low masses. Actually, they cross at around 50 GeV. Okay, and so LED feature 50 million boost because of the charge and no pileup. That's an advantage. But PP has 10 to the 6 larger integrated luminosities and has proton taggers. So basically, the takeaway message is that if you want to do photon-photon physics below 50 GeV, use LED. If you want to go above, use PP. However, to use PP, the two protons have to emit their photon, and they lose a fraction of their energy. And then this means that they get a little bit of stop, and they will slightly deviate from the orbit. And then if you want to tag them at 200 meters, then the photon energy loss has to be at least 150 GeV per side. So you start to have acceptance to tag the two protons from photon-photon above 300 GeV. If you care only of tagging one of the protons, you can go lower. Okay. Now what we do, as I will show you, and we do it here at 200 meters, those are the proton taggers. This is the central detector. And what we do is we do a coincidence between because now we are running with pileup, okay? PP, we are running with 20, 30, 50 collisions. So how can we tell? So what we do is we say we produce a gamma-gamma to gamma-gamma, level at the scattering. What we do is we do a matching of the kinematics in the central detector system with the proton kinematics. And by doing this, we can select the event. So the rule of thumb is that if you want to do SM or BSM with gamma-gamma, below 50 GeV, use LED. Above 300 GeV, use PP. In between, you can use both. And actually, now we realize in PP that we can play either with one tag or looking at objects that are exactly back-to-back and that have 0 other tracks associated with the vortex. So even with pileup, we are able to fish out this photon-photon collision I will show you in PP. Now let's give you some examples. So that's the first thing I want to cover here, production of a spin even resonances via photon-photon. So quarkonium, deuterium, Higgs, AUPs, graviton-like particles, whatever you want. So the first thing is that there is a very useful pocket formula to compute production of a resonance X with mass mx and even spin j, total width and given photon width. This is given just by the simple Breit-Wigner. You take the limit of the narrow width approximation, you get this compact formula. and from this you plug it into your code, and basically the cross section to produce a given central system X in gamma gamma is just simply this. There you have a spin factor 2 times J plus 1 times the diphoton width divided by the mass of the object square, and this is the 2-photon luminosity. Okay, so you can compute if you have the 2-photon luminosity, and you have it here in these plots I showed you before. This here, you just read off any value. You have a resonance at 10. You read off the value here. You plug it here, and then you know the width, the photon width of your object, the spin of your object, the mass, and you know the cross section. It takes 1 minute. So the first thing is that we have more than 70 scalar and tensor mesons that can be produced in UPCs. This is from the PDG with the resonance, the quantum numbers, the mass, the total width, the diphoton width, and the dominant decay, which is, of course, for the pi zero, for the pi zero is photon-photon. For the other objects, often it's not the case. But the first takeaway message is that those objects, the production of gamma gamma to pi zero, that's the Primakov basically process, or eta prime, or F0 is 0, resonance F2, A2, you name it. They're very large. They're in the multi-millibar range for LED UPCs. So, but nobody has measured it. CMS and Atlas cannot measure it because those objects, I mean, we are talking of object of 1.4 GB that decay into pions, kaons, very soft. So it's we're completely blind to this. Okay, we could maybe try, but that's not where CMS or Atlas are strong. Here, ALICE and ALICE 3 in particular, LHCb, should be able to do a measurement of all these processes. And the good thing is that if you check again, out of these 70 things, there are many, no observed gamma gamma decay, no decay, no decay, no decay. There are many objects that are spin 0, spin 2, even spin 4, but we don't know the diphoton width. So if we do the measurement of these objects that we know they exist because we have seen them in other decay modes, and we search for this decay mode in photon-photon, we can just reverse the formula and get the diphoton width. So if we have a cross-section in UPCs for a given X object, just take its spin and mass, and then you derive, you know exactly this from your code, so you can determine the diphoton width. So something at least 3 and LHCb could do is to determine the diphoton widths of many of these resonances. The same goes for heavier charmonium and bothonium states between 3 and 10 GeV. Here the cross sections are in between 0.4 millibars and 10 picobars. I mean 10 picobars is for the Higgs, okay, which is the heaviest one we consider. And most of these resonances are in principle accessible in LED or PP. Now this is 3 GeV is relatively heavy. We could see them in Atlas and CMS, but again, charmonium is probably ALICE and LHCb can do a better job because they have low PT, charged particle, and photon KD and RICO that we don't have. And the Higgs boson, we computed we expect 400 events at the end of the high Lumi LHC, gamma gamma going to Higgs in PP, but it's on top of a huge gamma gamma to BB very reducible background. So
what the problem with the Chi-C states, and I think the A to C, and I think the Chi-C, is there's a larger background from photoproduction of the Psi2S and the J psi, which then decay radiatively to gamma Chi-C, for example, and that is a much larger than the rate for producing things via gamma gamma.
Yes, you can. However, you can play as we were discussing before. First of all, gamma gamma is really at rest. Gamma Pomeron has a larger PT of the object. That's one handle you have. Another one is exploiting the spin of the particle. Those, I mean, any background which is not the spin 0 or 2 will have a different angular distribution of decay products. So, I mean, somebody has to do the studies, but in principle, one should try them. So, and some of these, like KV1 and KV2S, some of them have relatively, I have another table, but not here. We have the photon width is not super well known. It's not within 10-20%. So if we do the measurement, we can constrain the photon width of these objects. And then, of course, we can produce also C-even, not just C-even standard model, but BSM resonances, actions, and gravitons. Let me go now to the next one, because this is where we have actual data. So in CMS, for example, we have searched for this process that protons exchange 2 photons, produce an axion-like particle or a graviton-like particle that decays back to 2 photons. So basically, we are looking for the production of 2 pairs of photons back to back, above from the light by light. But at high masses, the light by light scattering is zeptobarn, is negligible. So basically, anything there is a signal. So what we did in CMS is in PP at 13 TeV. So what we do is we tag the protons in the proton taggers at 200 meters. So this already imposes that the object here has to be above 350 GeV. And we require that the 2 photons at mid rapidity are exactly back to back to within 1%. As I said, photon-photon fusion, these 2 photons are quasi-real, so this object has 0 pt. And then we do a matching of the mass of the central object and the kinematics of the 2 protons, and also the rapidity. And with this, I don't go into the details, we have, of course, a background of pileup PP taggings with QCD gamma-gamma production at mid-rapidity and so on. At the end, we expect one event and we observe one event, but this one event is background. But the absence of an excess allows us to set the stringent limits on axion-like particles over the mass range between 0.5 to 2 TeV. Okay, so this is a regime nobody had probed before. So we set limits in these couplings of the action, any possible axion-like particle coupling to a photon.
You said the continuum is very low, no?
Yes.
Because if you produce any resonance, the resonance dominate?
Yes, the continuum, I will show you, the continuum is the same, but instead of an S channel, you have here a box,
yeah,
and you have gamma-gamma. But this when you look to this process for 350 GeV, the spectrum goes like this. Is zeptobarn. It's 10 to the minus 20. It's 10 to the minus 20 bar, and it's completely negligible. So light by light scattering. So there is no other process that we know.
Just wondering why? I mean, the electromagnetic coupling is still same, right? You still have like 2 photons here and here come. Just when the event mass is large, maybe because there's because there is lepton. I mean, it depends on what is the loop.
In the loop, you have all charged particles.
All charged particles.
And these masses, you have W's.
These are very virtual particles. The
yes.
loop,
yes. You have top work even. These masses, you have W's and tops mostly.
That's because the suppression comes from that.
So you have a suppression with many factors. First of all, you have 4 vertices. So 4 times, alpha to the 4th. So it's 10 to the 5, 10 to the minus 9 to start with. Anything you start with this, you have already this factor. And then if you have heavy particles in the loop, this gets super suppressed. Maybe in the backup I have the plot. I can go show you. It's negligible. So, okay. I mean, we don't see.
But the signal should also be small.
Yes, of course.
Unless there's something
Of course, exactly. That's the thing. Yeah, that's the thing. We see 0. Okay, we see 1. We expect 1 from random coincidences of protons and photons. That's what we see. Okay, that's a very clean thing that you can do with protons. Now we can do the same thing in LED. But now we don't go to 350 GeV to tag the protons. We go to 5 GeV. Okay, this is the softest photon possible, and we require again 2 photons to be back to back, and then this is our data. The data points is our data as a function of the mass of the pair, the photon pair, number of events. We see 26 events. And this is the light by light scattering background. This is other backgrounds, QED and so on. And this, if we had an ALP of 50 GeV or 40 GeV to show up like this. So this allowed the fact that we don't have any count up here above 15 GeV, 16 GeV. Allow us to set the most stringent limits also again. So you see now that's the whole data of the coupling of the ALP to the photon as a function of the mass of the ALP. Here we have the intensity frontier, beam dumps, and so on, supernova, cosmological, astrophysics constraints on ALPs. Here we have LEP. And then here we have the data from the LHC. So Atlas in LED is dark gray, and then CMS now, the latest result, we go a bit lower. Okay, and you see that this range here is, we are the most competitive. I mean, lab basically was here. We are now 10, 15 times better than in searching for ALPS in this mass regime. So that's, yes.
So you did this for the mass range 5 to 10 GeV, which is where you do have
Yes.
background. Why didn't you go higher? Or?
You can go higher, but here there are other things. Well, what did they do?
Squeeze it.
Here we could, yes. I mean, the absence, there is nothing. We don't see any count up there.
Okay.
But in reality, the limit is about 160. I mean, it's very difficult to produce. The photon fluxes died down. So okay, yes, we could have gone here, but we just cut it because there are other limits which are more competitive. So, but indeed, we could have done something softer, but we are not competitive anymore.
This is the run to that run data.
This is 2018.
Yeah, so I see the interest. So what do you expect for the run 3?
Well, we have, this is mostly, as you can see, this is mostly dominated by statistical uncertainty. So unfortunately, we get 1.9 now. So we will get, what we will be doing is adding all the things. That's what we did now. We added 2015, 2018. So now we will top up every time. We'll be topping up. The problem is that with 1.6, we integrated this year with 1.8 inverse nanowatts. So yeah, we can, yeah.
Incremental.
We need a factor of 10 there more. We want to be, but what we are doing is adding previous results, and that's it. And also what we did, this was not done by CMS, but with there's a paper with 4 authors. What we decided is to recast, instead of discussing axion-like particles, what happens if we if we search for a graviton-like particle, so not a spin 0, it's spin 2. So naively, you take the pocket formula, you put here 2 instead of 0, and naively you expect 5 times more cross-sections for the graviton than for the ALP. But of course, I mean, an ALP you can assume it couples to photons mostly, so on. But the graviton, the most agnostic one, or graviton-like particle should have like some kind of universal couplings. And when you do this, you go from this cross-section, which is assuming 100% coupling to photons, to a 5% coupling to photons, taking into account the coupling of this object to other standard model particles, and then you go below the ALP. But still, okay, within this, we generated those events with gamma UPC. We plugged the first Pauli Lagrangian for graviton production in MATGRAPH. You see, and the idea of this is just to show you that if you have some BSM model or even standard model that you can plug in MATGRAPH, you can just plug it and compute things with gamma UPC. So any crazy idea you may have, you can compute it and show results. And those are now the best limits, the best upper limits sets on the photon graviton-like particle coupling from masses from 5 GeV to 1 TeV. Yes, 1 TeV, 2 TeV, and also the coupling is from 0.05 to 1 TeV minus 1. So that's a coupling, and that's the mass. All this was uncharted territory for this type of spin 2 objects. Now let's move to the other processes. Now you don't produce something in the S channel, you produce something in the T channel, like a pair of charged particles like leptons or quarks, and the 2 ions or protons survive. So here we focus on the first thing, the cleanest thing. Simplest thing is the Bright-Wheeler process, gamma to E plus A minus. Okay, this is the simplest photon fusion QED process you can think. What we do in CMS is we search for exclusive E plus A minus, so only a pair of an electron and positron produced, nothing else in the event, with masses above 5 GeV. That's where we can reconstruct things more or less safely in the calorimeters, and with a coplanarity of below 1%. The 2 objects are back to back, and and we compare. Here we have 20,000 events. We can do many things. The first thing we do is we compare to different Monte Carlos with different photon fluxes. And the first thing to realize is that, for example, the PT, so as I said, the coplanarity of this object is below 1%. The electron and positron are back to back. Their PT is very close to 0, but there is a small tail. And this small tail is due to FSR. So the positron or electron can radiate a photon here, and then they get a kick in PT, and they are not back to back anymore. So this is the data here. This is the PT of the pair, and this is the super chic or gamma UPC with this FSR, and without is a starlight, for example. You see that you don't reproduce the tail. So photon FSR is needed to reproduce experimental data, and you see here the cos theta star, or the rapidity of the pair, or the mass of the E plus E minus. You see we go almost up to 100 GeV compared to the different models. Okay, so the data is pretty good. It allows to discriminate between photon fluxes and between other things. So for another thing we can do with these 20,000 events is to look for the Breit-Wheeler process, but now where the one or both ions get excited because of extra photon exchanges, and then they get mutually excited electromagnetically, and then these lead ions emit a 0 degree or one or more neutrons, or zero if they are not excited. So with all these events, we are able to compare the probability of neutron emission for different neutron categories: 0n, 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 xn, 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 0, 1, 0n, 1n, plus 1n, plus, okay, all the combinations. This is our data in black, and gamma UPC, super chic, and starlight in other colors. And you see that the data models agreement is good for the 0n category, and plus minus 20% for the categories with 1n. And what we are doing now is doing really, we're studying the giant dipole resonance. This is the, but really at huge energies. You see here the peak at 8 MeV, and then I did my thesis on this in TAP. So I was in TAP, yeah. And then you see here, of course, at some point it goes down, and then you see here the you start to produce also now hadrons, so pions here, and so on. That's the tail. So this is the data of photon-nuclear excitation, but now we are probing this at ultra high energies, and there are improvements. So for example, in gamma UPC, we included much more data, and we have a better agreement for some categories. Now, another thing with Huasheng, he computed the NLO corrections. So this is so far all the calculations have taken into account the P channel alone. We added FSR by plugging a parton shower, but now Huasheng calculated the virtual corrections also, and the cancellations between real and virtual processes. So now we have, for the first time, we have these gamma-2 dimuons and di-tau at NLO QED accuracy. This reduces the fiducial cross-section between 3 and 5%. Mostly what happens is that if you emit a photon, it goes, this muon goes below the acceptance, for example. There are changes in acceptance and so on. So that's why we have a drop in the cross-section. It modifies the ecoplanarity, of course, if you allow for this type of processes. The two leptons are not back-to-back anymore, and so on. But takeaway message is that it improves the data model agreement, and now it's key for precision studies, because the measured cross-section for gamma-2 dimuons, for example, has very small uncertainties right now. And this is gamma UPC with the charge factor at leading order, the electric dipole at NLO, and so on. We get the best agreement with NLO with a charge factor. You see here is around 1. Okay, that's a ratio of data to theory for total cross-section. And then Atlas produced, extracted from the gamma-2 dimuon final state, you can reconstruct backwards the kinematics of the photons by looking at the mass of the pair and the rapidity. So if your dimuon goes in this direction, you know that this photon had more energy than the other, okay, and the other way around. So by playing with this, you can get the kinematics of the photon 1 and photon 2, and you can determine, per event, you can determine the minimum and maximum photon energy, and that's the spectrum that you get from the data. And this is for the comparison of data to Monte Carlo for minimum photon energy, maximum photon energy using charge form factor or electric dipole. And you see the ratios. Here they are very close to 1 for the charge form factor, very close to 1 for the maximum and minimum photon energies. whereas for the electric dipole, they are off. You see it here, they are off by 10 to 30, 10% at low photon masses and 30%. So now, starlight is using this type of thing. You don't see it in photo production because this is photon-photon goes square, okay? So the difference is of 10% means that your photon is off by 3%, 3.3%. Okay, things go square. So this is something I think that we were discussing over lunch. I think Starlight should try to implement the transfer factor and even for post-production studies. Now, something which is now very, very recent, maybe this is published since a few months, by exploiting gamma to tau, we were able to set the best limits on, best limits, because we don't see it yet, the G-2 of the tau lepton. So the tau lepton, since the tau is a short-lived particle, you cannot determine its properties like we do for the muon or for the electron. So the only way to probe the electromagnetic properties of the tau, the only way, one of the ways that's a way it was done at LEP, and it's been done now, is to go for gamma going to tau+tau minus, okay? This probes the electromagnetic moment, the magnetic moment of the, actually both electric and magnetic moment of the tau. So we had a first observation of this process in LED UPCs by hadrons and CMS in various decade modes, but now this is very new. That has been the first observation of the process in PP UPCs. And this is, even with high pileup, we look at events where the tau decay products are, the electron and muon are back to back, they have zero activity, so the vertex has nothing. And we are able to fish out this type of events out of the huge pileup background. So this is the number of tracks. Of course, here, di-tau is dominated by Drell-Yan, but then at low mass, when you go to zero, no other particle is produced apart from the tau. You see here an excess, which is exactly what you expect from gamma to tau. And then what was done was we put into MATGraph with gamma UPC a SMEF model with two operators that are sensitive to the moments of the electric and magnetic moments of the tau lepton. And we determined the cross-section for variation of these operators. And you see how the cross-section at high masses changes by modifying the magnetic moment of the tau lepton by 0.006 up or down with respect to, you see the effect, okay? So by looking at the production of this type of process at high masses, you're sensitive to G-2 tau. And that's how this was constrained. This is the current best measurement of this quantity. So we are not yet sensitive to the quantum term, the Schwinger term. So you know that this object is 2 in quantum mechanics. Now it's in classical, but there is a first correction due to QD effects, and this is called the Schwinger term. And this is 0.0016 is the per mil effect. And for the first time, we are approaching this. This is our measurement. A tau is per mil plus minus 3 per mil. Okay, so we are starting to approach to. Of course, there are other corrections. You go from the per mil to the per mil plus peanuts. This is due to electroweak corrections, the Higgs, and if there was BSM, and so on. So that's the most precise G-2 to date. It's 10 times better than LEP, and we are approaching the first quantum correction.
Yeah, but you're still consistent with zero, right?
Yes.
Errors, right? I mean,
we see, so we don't see any deviation with respect to the standard model. So that's we measure the cross section.
Sure, right?
Yes.
But the G-2 is also consistent with zero.
Yes.
As it shouldn't be, but as
It
according to your measurement, right?
We didn't measure yet.
Yes. Okay.
We didn't measure it yet. We constrain it.
Yeah.
But it's the best constraint that we have. Yeah. Yes. So last topic, gamma to a pair of electroweak bosons. The first one is light by light scattering. We proposed this like 10 years ago to discover light by doing gamma to gamma in LED. The analysis strategy is the same as before. We look for a pair of photons without anything else. In this case, above 5 GeV, which is you can reconstruct photons above 2.5 GeV, but at least on LHC should be able to do these lower masses. and we require the two photons to be back to back. And this is the distribution of acoplanarity. This is 0, and this is the in orange is the light by light signal, and that's our data. You see, I mean, there is a background here from different things. The Bright-Wheeler process where the electrons and positons are misidentified as photons and so on. But then at 0 acoplanarity, you have a jump. Here is from light by light scattering. And we have a significance of 5 sigma. And with very large uncertainties, is 100 nanobarns plus minus 30 nanobarns. So it's 30% uncertainty still. It agrees well with the state of the art of this process, gamma gamma to gamma gamma, computed at NLO QD and QCD, which is 95. So there is a calculation now that modifies this by a few percent. Okay, and then my last slide before the summary, we can do also gamma gamma to gamma z and zz and so on. The cross-section in the standard model are attobarn, 65 and 40 attobarns. There is this tiny, unless there is some BSM that enhances these anomalous quartic gauge couplings. And this has been, there have been some operators, some SMEFT approach that put some operators to modify these couplings and so on. And what we did also in, sorry, this is a proposal, sorry. This has not been measured. What we have measured is gamma gamma to W plus W minus at high masses, where now the W plus and W minus go hadronically. So those are like fat jets, it's called, because those two guys are super boosted and merge into one jet. At very high masses, 1.1 TeV, with proton tagging, you see here, we do matching and so on. Okay, we have a fiducial cross-section, which is smaller than 67 femtobarn, which is far away from the standard model, but that's a very low cross-section, and sets limits on dimension 8 anomalous quartic gauge boson operators. With this, I come to my summary. Photon-photon collisions at the LHC. So the LHC is a unique photon-photon collider with the largest cross-sections ever probed, and we can study masses from 100 MeV to 4 TeV through different complementary means. The first one is with lead at low masses between 5 and 100 GeV with 0 pileup, so ultra clean events, an event with just 2 particles produce nothing else. You can use UPCs at intermediate masses between 50 and 300 GeV, but with a small number of tracks or 0 tracks associated with the vertex and acoplanarity 0. And then at high masses, we can tag the protons, okay, above 300 GeV. And there is an increasing number of measurements performed. So gamma gamma to dileptons. This allows us to set constraints on photon fluxes, on neutron emission probabilities. This has allowed us to the first observation of a rare standard model process like light by light scattering or G minus 2 tau. And we can set competitive BSM limits in some region of phase space for axion-like particles for massive gravitons, anomalous quartic gauge couplings, and so on. I told you about improved theoretical predictions with few percent uncertainties. This is now true for all final states. We see even resonances like fermions, like bosons. We have realized that the charge form factor is the preferred photon flux, that we have parametric uncertainties control within a few percent, and we are able to compute NLO QD and or QCD corrections to this process, gamma gamma to the electrons, gamma gamma to tau top anti-top. I have a backup if you're interested in this. And I close with this. We observe light by light scattering. We set the best limits for alps and gravitons, and we have the best measurement of G minus 2 tau, and all this exploiting this fancy type of collisions at the LHC. Thank you.
Right back, I don't know the latest thing. This mu and G minus 2, the light by light scattering was one of the things one needed to know.
Okay.
I don't know what the situation, whether this is under control. Could you make a competitive measurement with this? I mean, you probably have to go down in mass.
Exactly. Yeah. People have asked me this several times. So you're perfectly right. So it's the hadronic light by light, which is the nominal uncertainty. And what we should do is, yes, we should go through all these. When people do the calculations in the lattice today, they are plugging all these particles. So now we do it, but instead of using lattice, we use latex. So that's why one very good motivation to try to do this in LHC.
But then you need Alice for, you guys
Yes.
cannot do this.
Completely blind to this. Well, if it is a neutral final state, it's impossible. If it is charged, we could try it. If it's with pions and kaons, we could try it. But as soon as you have some soft photon, forget it. Our noise thresholds are 1 GeV.
Other questions? One online? Oh, Simon.
Hi, David. Sorry I couldn't make it today. Very nice talk. I was
Thank you.
wondering if you could go to the slide with the Alps, like at high mass, with the Roman pots. Yeah, this one, yeah.
Yes.
So I was wondering if you can clarify this for me, right? So if you go to high invariant mass so at low invariant mass, like it's super interesting because the normal QQ bar production, QQ bar Alp plus photon, in a normal LHC runs, you're very limited by triggers and background rates, and you really can't do this search effectively. But if you go to very high invariant mass, like 500 GeV and higher and so forth, you could just look for 3 very, very hard photons in QQ bar going to gamma Alp decaying to 2 photons, and you'd be background free, basically. The trigger would be trivial. And I don't know, is that something that has been done, or am I missing something? The rate for that should be higher, right? Because you're not paying the photon PDFs at that point, you're just using QQ bar.
Yes, but you have the triphoton QCD background. There is an irreducible background, a continuum. You have triphoton.
At those energies, it's essentially negligible. It's like a couple of femtobarn. It's 10 to the minus 3 femtobarns or something.
Okay, but this one, as you know well, at high masses is even lower, and light by light, pure light by light is even many orders of magnitude smaller. So I agree. I mean, I'm not trying to oversell this. It's true that you could try to look for this in other channels, in hadronic channel, in partonic collisions. Indeed, if this object exists, that's a typical question. I mean, why didn't we see it in inclusive searches? No? But that's a particularly clean way to search for it. But I agree with you. There are other. So you could look into partonic production mechanisms. And yes, and if this object exists, it should have appeared there. But okay, I mean, you guys were the first to propose the Alps in UPCs, so.
Yeah, I always was very excited to try to find more ways of using the Roman pots, right? Like, it's really interesting to see if there are any other sort of channels. But if found it difficult, yeah. I mean, this sort of works, but you have to fight against QQ bar. Just like the general run is very effective there. Okay, thank you. Yeah, I just want to see if anyone.
But the triphoton final state is with surviving protons, you said?
Yeah, so you just have QQ bar going to a virtual photon, and the virtual photon goes to a photon plus an Alp, and the Alp decays to 2 photons. So it's the same coupling that you're using here.
Yeah, but
you get 3 photons.
Break.
Yeah.
The protons
break. Yeah,
the
protons break.
Yeah. Okay.
Yeah, sorry, thanks.
No, thank you.
Good question. I have one. So this tau G minus 2 with protons surprised a lot of people when it came out. That protons are so much better. Can you comment on sort of why?
Yes, the reason being is because at least, I mean, the type of modifications. So a G minus 2 tau different than the standard model value would introduce a change in the cross-section at very high masses that is not visible in LED. Basically, LED we stop here at 100 GeV, and here variations of G minus 2 tau do not imply I mean, there are differences, but they're small. They're below 5%. Whereas up here, you have differences of 20%. So basically, at high masses, any operator that modifies the magnetic coupling of the tau lepton induces an increase in the cross-section that is not in the LED, does not appear in the LED case. In the LED case, you have modifications of a few percent, and it's tricky. Whereas here, that's a gain factor is by going to high masses.
Is there a simple reason to understand why the modifications are largest at high masses?
Maybe Simon can comment why. I mean, if you modify the magnetic moment of the tau, is this something? Is this a property of the of these effective operators? Do you know,
Yeah,
Simon?
it depends how you parameterize the effect. So if you parameterize it in terms of a higher dimensional operator, which is usually what people do in terms of SMEFT, it's a dimension 6 operator. So basically, the effect always grows with energy. So you have in the PP collisions, you have luminosity at much higher energies than at heavy ions. So like you essentially, yeah. So it's a cross section that's growing. If you had an arbitrarily large energy collider, it would eventually become bigger than the standard model rate.
This is model independent. Maybe Spencer is the question: is this correspondence between the operator and the G-2 tau univoc, or?
It is under the assumption that whatever is generating the modification to the G-2 is physics that's too heavy to be probed directly. So in other words, you're taking the limit where the particle that runs in that loop is quote unquote infinitely heavy relative to the collider energy. Yeah. So in that case, like it grows. If you take it lighter, then it becomes more model dependent, and it would there would be a feature. It would be a hump essentially in some sense.
But is there I don't know, I'm just guessing, is there possibility of BSM physics at low masses which could induce a different G-2? I don't know.
Yes, but it's very, very, I tried this, but like it seems extremely difficult to get an effect at this size, unfortunately. The only thing that I can think of is if the tau itself is a composite particle, it is a bound state, because you can't afford to pay the loop factor. So the tau has to be a composite of two other particles, and so then it might have like an intrinsically large dipole because there's two charged states in there. I'm not aware of a lot of good models that do that sort of thing, but that's the kind of, if you were to see a deviation of the size that we're talking about here, I would think that would point to the tau being a composite particle of some sort.
Thank you.
I don't have a lot of money on that, but like that's I think what it would mean. Yeah.
Other questions? Well, we had a bunch during the talk.
Thank you all.
Again.